What works in machine learning? It's actually really, really simple. Right? So that is hopefully the lesson that you've learned in IML. Right? That is the equation for the support vector machine. And throughout your coursework, you've probably seen that works out of the box better than just about anything else that you can try. Okay, and that is a relatively sad state of affairs, right? To say that machine learning reduces to basically that. Whatever you want to predict, you got your representation of the data x, and you learn the weight vector y, and you take and you see if that's bigger than 0 or smaller than 0, and that's your classification. If you want to classify, if you want to do regression, then you remove the sine function, the squashing function in front, and then you just do regression. Right? Great. So machine learning solved. And that is true to some degree, because you have algorithms like the support vector machine algorithm, which can learn extremely effective set of weights. They're just really, really good at finding the right set of weights that is very robust and can generalize to new data, and in general just performs really, really well. But there is a very big if, and that if is you have to have the right x. That only works if you are able to take your data and convert it into the right attribute value representation. Only if you extract the right set of features for the data does learning work. And remember, we had a whole lecture on how you convert your input data to features. And unfortunately, for different kinds of data, you need very, very different kinds of features. So if you were trying to do speech or music, waveforms of any kind, you can't just take that and use that as x. It will not learn anything. You will get garbage out. What you need is some spectral representation. So you do a Fourier transform on the time series, or you take MFCC coefficients, and then you use those as your x, as their representation that goes inside of your support vector machine. And everything is great, but you need to know how to do that, right? And that requires domain knowledge. And if you were doing images, again, you couldn't just take pixels and stick them as your x values. Your support vector machine would not learn anything. You need to represent it, and there is an entire field of computer vision dedicated to how you represent images. So maybe you'll sort of extract a shape and compute some sort of features over the shape. So maybe the curvature of the shape or the projection profile of the shape. Then maybe you'll take the image, slice it up into a little grid, and for every element in the grid, compute some summary statistics again. So you could look at the color distributions, right? What is the histogram of the basic colors in each one of those grid points? Or you could say, well, maybe what are the edge features? So you take a bunch of edge filters, you pass them over every segment of the image, and that gives you a distribution of how many times in that corner of an image did I see a vertical edge or a horizontal edge. And again, you get a histogram of those edge counts, and you can use that as input to your learning algorithm X. So that's great, but you need a computer vision expert to know how to compute curvatures and how to apply edge detector filters. So you need domain knowledge, and that is slightly disappointing, because what you would like to do is you would like to have a universal learning algorithm, something that could get the right representation no matter what data you were dealing with. So really, at some level, the question is, could we create an architecture, a learning architecture, that is able to represent any kind of data in just the right way for solving pattern recognition problems? And the good answer is yes, resoundingly. Every single one of you can create a learning architecture like that. The answer is actually really, really simple. You just have kids at some point. Okay. Humans are universal learning architectures. Humans are able to represent whatever kind of data you throw at them in just the right way for solving any kind of pattern recognition problem that you force them to solve. They're lazy, they don't like to solve those problems, but if you force them, they can solve just about anything.